her PhD from Aizer Mohali and today's from Thank you. Thank you for the introduction. So yeah, as she said, I'm a postdoctoral fellow in Michelin Group for a past 12 months now. And my tenure is ending on 31st March, so I'm like really there for 3 4 days. I'm going to leave the campus. Yeah, so again, thank you for you that you show up on the weekend and completely do that. So today's topic is aspects of glaciation, clustering, and structural formation in the universe. So there are 4 fundamental forces in the universe, and gravity is weakest among them. And I mostly work with the gravity. So just to give you an idea, the strong force, which is nuclear force, and the gravitational force, the order of magnitude difference is 10 to minus 38. So that much weak is the gravity force. And another particular thing about gravity is it's a attractive only force. So because of which we see the matter in the universe at different scales comes together to form a different variety of structures. For example, if coming matter is balanced by atomic and molecular forces, you get a planets. Similarly, if it is balanced by nuclear fission energy, you get a stars. Then velocities, that is kinetic energies, you get the solar systems, then galaxies, and cluster of galaxies. So what this plot shows is, so this is a length scale in a 10 raised to this number in meters. So typical size of Earth is 10 raised to 6 meters. So similarly, these are typical sizes. So the galaxy clusters, their size around 10 raised to 24 meters. Now, what if we look beyond these scales? Right? This is order of like megaparsec, 10 megaparsec or 30 megaparsec. So we use a megaparsec unit in astronomy. So what if I try to look what is the structure beyond this scale, like 626, 30 or so? So people carried out a survey for that called galaxy surveys. So this is one result from such a remarkable galaxy survey called SPSS. So so we are here at the center, which is Milky Way's location, and this is galactic north and galactic south. So this is how galaxies are distributed around us. Now you see, these are not this is not some random distribution that I throw a dust and whatever pattern. There are some features in it. There's clumps of matter and this giving a feel like it is a wave kind of structure. So this is called as cosmic wave, or formally it is called as large scale structure. Now good part is we believe that we understand theory behind it, so that these theory equations we can give it to the computer systems and simulate these structures using supercomputers. So when you do that, you get this. This is one result from my simulations. So you see, these two structures, I will say, these are statistically similar. Those are not exactly same, meaning you cannot point anywhere in this picture that this is Milky Way and exactly you will get the same map like this. But what I am saying, it is statistical similar, which means if I draw small circles of this size at different locations and calculate the average dispersion in those circles and do the same exercise here, they will match. So any statistical quantities like solar homogeneity, power spectrum, will see those that we calculate here and here, those will match. So that's what I mean by statistical similarity. Yes. So this is a simulation. This is a simulation. This is observation. Right. So where do you start the simulation? Where so like at what point? So I'm assuming this is with time evolution, right? Yeah. So this is at present time. Okay. And this is also at the present. Right. So where did you start this simulation? At very early time. So if you know in the redshift terms, so it will be 150, 100 redshift. So those are very like Gaussian, non-linear kind of initial condition, and then it evolves through your system, and this is the present. Now, there are like particular features of this cosmic wave. So you see, there is lumps of matter. Then you see in both of the structure, then you see the thread-like structure called filaments, and there is empty regions called voids. So we study these kind of structures, and mostly I study these lumps of matter called gravitationally bound structures of matter called halos. So this is the topic list that we'll try to cover. So this is setting up some basic background, and these are the three categories of work. Sorry. Okay. So these are three categories work, which are categories in which we'll see how much that we can cover. So let's start with the basic background thing. Now, the universe is spatially homogeneous and isotropic, and it is supported by observations. And such observation is important to do cosmology from general relativity. So, in such a universe, which is spatially isotropic and homogeneous, which may expand or contract with time, the distance in such a universe is given by this d square. So you see, this is in your spectral coordinate system. This is your angular part. Yeah. This is a radial part scaled with some factor with kappa. Then this is a time dependent part which tells you about the expansion or contraction and the time. And both the time part and space part has inverse signature because this element is your frame equivalent. Your physics cannot be the frame equivalent. So this is the line element. So once you have such a line element, so notice only quantity here which depends on t is a, which is called the scale factor. The kappa is something to do with the curvature of the space. Now, so with this, the expansion of the universe is, since only t dependent quantity is scale factor, is governed by these two equations called Friedmann equations, which are nothing but the speed with which universe is expanding, and second derivative, the acceleration with which universe is expanding. So on that side we have the first and second derivative of scale factor. On the right side we have the energy density in rho of the different constituents of the universe and pressure P of those constituents. Kappa is the same kappa. We'll set it to 0, again supported by the observations. So throughout all this presentation, this will be 0, so this term is not there. And this is lambda called cosmological constant. We have to include it to be consistent with the observations. Next is, so now, so if you combine these two equations, you get this equation, that is how energy density of constituents of the universe evolve with the time, and which you need to solve with the equation of states. So if you, for different constituents like photon, matter, dark energy, if you put their corresponding omega, you'll see the photon energy density decreases in a power 4 with a scale factor. Matter energy density decreases in a power 3. Lambda being constant, also known as dark energy, stays the same, and this is not there for our case, but if for some cases it decreases in power. So this is the plot. On x-axis you have a scale factor, and these two blue lines, but dashed and dotted, those say the contribution to the total energy density, one by the dark energy, other by the matter. And since they both vary with the different rates, there exists a time where they contribute equally to the total energy density. And such a time, or we call it as epoch, separates the matter dominated era and the dark energy dominated era. Similar equality era exists between these two components at very, very early times. Those separate radiation dominated era and the matter dominated era. Which brings us to the timeline of the typical timeline of the universe. So at the beginning, the universe undergoes rapid expansion called inflation. After that, there is a formation of nuclei, then radiation dominated era, then a form of recombination where stable atoms get formed and universe becomes transparent. Then before that there was onset of matter dominated era. Then there is dark ages, meaning there were no sources of light for very, very long time. The universe were dark. Then there's beginning of formation of first sources of light somewhere here. Then there is a reionization, and currently, very recently, we are entered into the dark energy dominated era. So we are here at the present. So during radiation dominated era and early matter dominated era, the problem of structure formation was in the linear region. What I mean is, so the entire universe has some density of matter, and if I consider a small portion in that universe, so the density within that region might be little off. It might be little higher, little lower. So that we call as a perturbation, which is nothing but this delta. So how your in the considered region, what is your density compared with the background density of the universe. So when this quantity is very less than 1, we can solve structure formation equations using pen and paper. Those are second order simple differential equations which you can solve. When the problem enters in the non-linear regions, where this amplitude becomes larger than 1, the more coupling happens, meaning the different sizes of perturbations start affecting each other, and then you cannot solve this using pen and paper, and you need a numerical method to get the answer, which happens in the blue region here. It is called the non-linear region of the structure formation, and obviously there is some overlap where you can have half part theory, half part simulation. So it's called quasi-linear. So quasi-linear region. So let's see. Let's take some example perturbation and how it grows with the time. So you have again scale factor, which is a proxy for the time, and on a y-axis you have a perturbation amplitude. Now there are two kinds of matter in the universe. One is dark matter, which only reacts to the gravity, and we cannot see it directly through our eyes. And another is a baryon matter, which is dashed line here, which is the basically all the galaxy stars that light we see is formed out of baryon matter. So for the dark matter, the perturbation amplitude undergoes it increases with the different slopes in different regimes of the structure formation, and ultimately it hits to the perturbation amplitude of 1, and this enters into the non-linear. Baryons, on the other hand, which are coupled with the photons. So as soon as baryons try to come together, there is a photon pressure which is increasing. So it is trying to push away that perturbation. Then again it is trying to come closer. Then again trying to push away. So you get the oscillations in the baryon matters. Those are so basically this kind of perturbation amplitude. This will eventually form a Milky Way size object. So these oscillations happen up till the epoch of recombinations, where what happens? Your stable hydrogen gets formed, and suddenly the size of the scattering section is going to reduce, and there is a free photon streaming is happening, which we still receive today. And basically, then these perturbations in the baryons gets wiped out. Then these featureless baryons quickly catch up the dark matter and forms a visible structure that we see in the potential waves of this dark matter. But this is a linear story. What happens in a non-linear case, as soon as your perturbation amplitude hits the non-linearity, something like this happens. The collapse gets accelerated rather than this linear case. The dark matter, there is a rapid non-linear collapse, and since dark matter can pass through each other, there is this oscillations, and there is the finite size object of dark matter that gets formed. This is called process of virialization, and this is how the dark matter shadow forms. The baryons, which is inside this dark matter, so it also undergoes the nonlinear collapse, but it has a pressure. It cannot pass through each other. So there is a shock, and then it cools down in the same dark matter halo, and then try to relax. So how do we know this if we cannot solve the equations? Obviously because we have done a numerical experiment and we have examined this part with the n-body simulations. So this is a full non-linear equation of the structure formation. So you have the second derivative of your perturbation, then the Hubble flow, and all the source terms here. So in the linear case, where delta is very less than 1, this part is gone. This part is gone. So your source by grad square of y, which you can put using partial equation, and this equation can be solved, but this is a full log linear equation. We need to take help of the simulations. So let's see what are these simulations. So simulations, so it is nothing but the Newton's law, again second law. So you have positions of, let's say, n particles. So the acceleration of those particles is supported by the potential. It's normal Newton's law, but the difference is now it is for the set of n particles. Okay. Now we need to put these particles in some representative volume in the universe. Such a volume should be small enough to avoid the GR correction. So, like basically that is below Hubble radius. Hubble radius is typically around 4 units, and it should be large enough to be compared with the scale of volume. So let's take such a volume. Now we need to put the particles into there. Before that, so real universe is infinite, but we have selected a very small portion in it. So what we do, we repeat all these boxes in all 3 dimensions. So we have created an infinite universe, yet we have to worry about particles in this box. So what happens if some particles evolves and get out of this box, the same particles the similar particles get entered. So that is called periodic particle. Now we need to put the particles such that those should be consistent with the observations. Now the initial time, the matter distribution, where the follows the Gaussian distribution at each separate mode. So for that we need a power spectrum. So what is a power spectrum? So you have each mode, each scale basically is separately Gaussian, with mean equal to the background density of the universe and dispersion given by the power spectrum. So at each scale, what power you have, that gives you the power spectrum function. So these are examples of straight line power spectrum. So it's a -1 power spectrum, and how straight line power spectrum, and how the distribution looks. As your slope gets steeper, there's large variation between different scales, and you see the significant -1 and -2, where the variation in powers is very large here, and even if you go to n equal to 0, you will see something like white noise that you see on the old televisions. Right? So these are example straight line power spectra. The real power spectra is something like this. So if you extend it, this looks something like this. The bell shape is called bell shape power spectra, which is very close to the what is the observable universe is. So on the x-axis we have frequencies or corresponding scales, length scales on the y-axis, and corresponding clustering power, the power spectrum amplitude on the y-axis. For example, in this example power spectrum, the clustering at 1 megaparsec is smaller than clustering at 10 megaparsec. So this is how we interpret it. Now, consistent with this, let us distribute the particles in our box. And now next task is for all individual particles here to calculate the Newton's inverse square law, force, and kick the particles. Go to the next time. And you keep repeating this until your desired time. So during course of evolution, you see the overdense regions get more overdense and the underdense region get more underdense. So this is about dark matter density field evolution. So which you see through how the field is evolving. Similar thing we can quantify using power spectrum. So same frequency that's corresponding length scale on the x-axis and clustering power. This is the initial time which we have given to the simulation, and this is how power spectrum evolves during your time as time evolves. You see there is a generation of power at small scales which slowly get transferred to the large scales. So this is a dark matter density field. We don't get to see it when we look up in the sky. What we rather see is something like this. A biased light that is coming from these dense regions of dark matter fields. So what is biased light? So very good example of it during Diwali. NASA publishes that picture of the lighting, and you can trace the India map that light. So what we can say using that map of India, where there is a light, there is a population of people. But where there is a no light, we cannot say there is a population there or not, because there might be some village where there are no street lights and that might not appear in that plot. That is called the bias principle. So where there is light, there is a dark matter. Where there is no light, you cannot see. That what bias means. So yeah. So these are some periodic objects which we see, the galaxies and so. Observers call them galaxies. We will call them halos. So which brings to my first category of work, the halo mass function and halo shape function. So what is halo mass function? It is a number density of halos or galaxies as a function of mass and time. Or redshift z or scale factor a. So t, z and a can be alternatively used for time. Now there exists a nice theory derivation for this quantity. To understand that, let's see how one such object, one halo gets formed. So this is one halo which I have tracked in my simulations. So you see center dark patch is the finally currently formed halo or a galaxy. And as the patch gets bigger or color gets lighter, the same set of particles tracked backward in time. So this initially arbitrary shaped patch, it seems that overcome the expansion of the universe, came closer and formed this gravitationally bound halo. So this is how one halo gets formed. But this is very arbitrary shape. For doing theory, we have to do very simplistic assumptions. So like this famous physicist approach, we'll consider this as a spherical cow. So those who don't know reference, you can internet search later. So let us see. Let us assume this initial perturbation is a spherical in shape. Now this is perturbation. Universe is expanding. This is also growing. Now what spectral collapse calculation says, if the perturbation amplitude within this region is larger than certain threshold, then it will expand with the universe, but it will halt at some time, and this will the gravitational pull will overcome the expansion of the universe, and this will collapse to form a halo. So once you know this theory, now it is now I did. So this is the spherical collapse is giving you how one halo is formed. Now to identify how its mass function, basically how at different locations, what size mass halo or those forms, it is now tasked to go to your initial matter density field and see where are the regions which crosses this threshold value and just count those. So once you count those, since we know initial very early time the field were Gaussian, we can calculate this in theory. So when you do that, you get a number density of halos as a function of mass and time, something like this. Okay, so this is the delta SC, which depends on time, which is what I was talking about, the threshold value within the perturbation. So this is that threshold value, and it depends on different components in your universe. So how much matter is there, how much photons are there, how much dark energy is there. So those kind of quantities affect these. And the another quantity is called root mean square fluctuations in mass. So basically you draw spheres of different sizes and draw these are different locations, and you will get a variations in this with respect to the average matter density. So this is that quantity, and it depends on the power spectrum. Different power spectrum gives you this value differently. Now you define this variable, which is like this, delta SC divided by sigma m. Once you do that, this quantity in the box becomes this, which you can notice is a simple algebraic equation. There's no mass, there's no time, there's no any cosmology like omega photon information, how much photon is there, how much matter is there. So this is simple algebraic equation. where you have a one linear function multiplied by the exponential cutoff, something like that. The linear function exponential cutoff. This is for spherical collapse. It is simple. This whatever I have explained to you. Now, in a realistic case, you just see the buttermesher always might not be the spherical, but somewhat ellipsoidal. So, if you incorporate this, you get this function modified like this, which is again algebraic function. This P and Q are just the fitting parameters to your solution. So, since these are algebraic functions, what is believed is that no matter what power spectrum you select, which means no matter what initial density field you select, no matter what cosmology you select, how much matter you are putting, how much photons, no matter what, you are going to get the same mass function because this is just the algebraic mass. So that is what belief is. Now my first one found that is not true. So this is different straight line power spectrum whose slope is given on the x-axis, and these fitting parameters, this P and Q, those are shown here, P and Q. And see, there is a trade. If those were to be universal, they should be a constant with the slope, something like this red line. But instead, what we found, they follow a trade. That is one finding. Those were the straight line power spectrum, which is not our real universe. The same study can be extrapolated to the real universe, and when we do that, this green one is our mass function, and the red one is what is there in existing literature, and what we see in the real universe, which is called as a lambda stadium universe. So our mass function fits better to the data, simulation data, especially at later time. This is current time, this is some earlier time. These are our findings from first one. Next is to we tried so our halos are not spherical. So reason behind why we find these trends is because tau's are not spherical. Right? Those are halos are really of very different weird shapes. So we wanted to quantify the statistical distributions of shapes. So we have a halo. We tried, meaning a set of particles which belongs to the halo. We tried to fit a ellipsoid to it. So in an ellipsoid, you have a three axis A, B, C in a ascending order. A being the largest, B middle, C the smallest axis of the ellipsoid. And then you take the ratios of this. Q is the second largest axis of ellipsoid divided by the largest. S is the smallest divided by the largest. So these are two independent quantities with whose distribution we can see. So you see that. So this is again the scale variable mu. The Q, this ratio, S, another. And these are different simulations with different slope of power. And all these nicely fall on top of each other. So we see, unlike mass function where we saw deviations from the universality, we here find the universality in the halos. Further, if you segregate the halos, right, in the elongated cigar-shaped halos and the disky shaped halos, which are formally quantified with the traction, right? So oblate halos, which are the first two axis lengths are of the similar order, and the last one is very less, which means you have a disky shaped axis. And prolate, which is another case where the other two, the smallest two are of the similar order, and the longest one is very long. So you have basically this is a elongated halos, and this is a disky shape, and these are inverted. So when you separate these kinds, you see the individually also they are self-similar. They are all different models fall on top of each other. Now this is interesting. So this is Q, S, the axis ratio, and this is the contour circle represents the 68% of most of the population of at that time. Time is given by this. So the yellow is some earlier time in the universe, and as your color gets darker, This is the later line. And these are three regions: the elongated prolet shape, triaxial, and discrete oblate shapes. So interesting is, as your cosmic times increases, the population of halos goes from elongated prolate to discrete oblate. Now that is one key reason, and we don't know why this is happening. So our next task is to see why this is happening. So that is something in the ongoing work. Second category of work is the numerical artifacts. So we have seen this slide earlier. So we are seeing the periodic boundary, which means the perturbation size. So if I have a perturbation of this size, that information is not there. Because if I draw this circle here, this circle here, this circle here, I'm going to get exactly same value, because that's how I constructed it. The periodic boundary condition. The variation will be exactly same, meaning it will be 0. But that is not true. It will have some value at the box scale. But we have cut the power spectrum at the box scale. So these missing powers, those are not represented in this. So those are going to create errors in this distribution. Similarly, how many particles I am putting in this box? If I am putting n, 2n, n square, whatever number I can put, that decides the mass resolution of this simulation. Because of which, on the I talked full term. So this is box size effect, which are missing perturbations on the large scale, and these are the missing perturbations and on the grid, or the smallest scale that can be resolved in the simulation. So missing these powers can create errors in these distributions, and we have to be sure about these missing things should not affect whatever results we are quoting. And because of this non-linear things, this missing power do not affect the quantity at this case, but they start affecting on these scales also, where we actually have a representation. So in this, firstly, we quantify the mass discreteness effect. Basically, what happens, how much are the errors if I do not consider powers below the mass distribution, or the smallest scale that can be resolved in the simulation. This is the errors in the RMS fluctuations. The solids are the full thing in calculation, whereas the dash one are with the missing small scale power. And this is for different initial conditions. Now you see, this is the resolution grid scale, basically size of single particle in the simulation, at which these errors vary from 10% to 50%, which is really very huge. So we should not quote results at a single particle level. This is a mass function saying the solids are the full calculation, and the dashments with the missing small scale power, and this is the mass and the number of objects with that mass, and number of simulation particles which forms this mass is there on the bottom. So you see, as your number of particles in the simulation increases, this errors increases. So to get more and more correct representation, you should have as many as particles in the simulation. But then your computational cost goes up. So we have limit based on what supercomputer we are available with. So then you can use this plot as a template to see halos of particular mass with what number of particles can be tagged as a result. If halo do not have that many particles, we reject that coordinates. That is one effect, the discreteness effect. The other side of effect is box size, missing perturbation beyond the box space. And these are complementary to this mass scale. So these increases on the small scales, these increases on the large scales. So these are very complementary, and these are very well explored in the literature. And it is believed those mostly affect the large scales. So what we are doing is, missing this case, we are trying to find how much it affects on small scales. So for that, we design a special suite of simulation who have same mass resolution, meaning we get rid of the mass discreteness effect. Every simulation has same mass discreteness effect. And on the box side, we choose different box sizes. So this is 250. At each time we go half and 125, half. Right? So we have different box representations. And when we find this hello shapes B by A and C by A with respect to mass of the halos, since dashed one is with the largest box which have maximum representations of modes on the box space. And the solids are these different cuts at the different boxes. So apart from the last box, which is 32 megaparsecs, the other three looks fine. And this is 2 to 3% difference. And we are in the era where the era of precision cosmology, you might have heard the era of precision cosmology, where we are trying to bring every error below the 1%. Given that this is 2 to 3%, that is a significant. So that is another work in this category. And the final thing, which is about the cosmological tensions. So we know universe is expanding, but there's a debate with what speed it is expanding. Right? So there are two kinds of measure which can two kinds of measuring techniques which measures the speed of expansion speed of the universe. So one is early type measurements, which is coming from CME. One is late type measurements, which is directly coming from the local measurements around the Milky Way, objects around Milky Way. So this early type measurements, which is CME, which is very early length, that equal to 11, like a few million years, and this is like some 13.4 billion years. So it's really very early. You can, and this is very precise. This is the most precise measurements in the cosmology that we have, and we calculate the speed of expansion here, and then we need some theoretical model to extrapolate that value to the present value. That is the early time measurement. The late time measurements, you need to fit this law. So universe is expanding. So you need the distances and velocities of distant objects. So you can measure those objects' distances and velocities with the telescope. Fit this law, you will get the answer. Now there is a discrepancy between these two. So there is an early type measurement, late type measurement, and they do not match within the 5 standard deviations. What it means, if I repeat this experiment 10 billion times, only 4 number of times I will get this kind of result, which is very rare. So that's why this is very significant difference between them, and people are trying to solve this every possible way. Some people are questioning these very few. This is very modern, precise measurement. Very few question this. Most of them are questions this, that our model of the universe may be wrong, and people are tweaking it. And some fraction of people also question the way these measurements are done. Now, what we have done is we go to our simulations. In real life, you have only one observation location, that is our Milky Way. So, being at a Milky Way, you measure the velocities and distance at different galaxies and fit Hubble. So, we have only one measurements like that. But in simulation, you can go to the multiple locations and do this exercise. So you let's say this is example observer. You draw the spherical shape around it, and measure. You know their distances, you know their velocities, and you sum over this thing, basically the individual object ka halo thing. Meaning velocities and distances. You get a 1 h0 in this shape for this observer. Now I increase this shape. Right. So I measure for given observer, I measure h0 at different spherical shape. Basically as a function of distance. And I can do that for all these halos representations. So I get distributions of h0, local h0, as a function of distance. So which looks like this. Right. So this is basically color is showing the distance within which particular h0 distribution is calculated, and this is the deviation in h0. Basically, the correct full value is here, and this is the deviation from reference one. Reference one is flat, which is the early time measurement, and this is the other late time measurement, the shoes, and this is what we get. So as your distance increases this way, your PDFs get narrow. This is expected because as you go to the distant object, your expansion velocity is going to dominate over the local motions. So that's why you see this narrow example. Then we find interesting thing, that is a correlation between where you reside and what Hubble you see. So this is the density field, and the red ones are the observers which see H naught lower than the reference point, and the green ones are so sees H naught higher than the reference point. And by looking at it you can see the greens ones are scattered or kind of void regions. On the other hand, the red ones are inside the clustered things. So already what this is suggesting, your H naught going to get biased whether you reside in underdense region or the overdense region. So that kind of solution we try to put for the Hubble tension, but this exercise can accommodate for up to 5% of Hubble tension. The total Hubble tension is around 9 to 10%. That was the last slide. Just to summarize, the linear theory of structure formation, that is based on the homogeneity and the isotropy of the intervals, and it gives some simplified results. But for the full understanding of the structure formation, you need to have a nonlinear studies using simulations, in which we studied a large scale statistics like Hello mass function, peculiar velocities, which is nothing but the Hubble constant, and a small scale physics like Hello shapes. Right? Yeah, so that's it. Just a last thing. So this is one story, the science fiction story. It's very small, 3 pages. So if you scan this QR code, you will get to read this. So you can send me feedback on the